Alright, so let's continue with our review of linear algebra. I have, okay, this is the part where I need to swap displays. There we go. So I have introduced vectors already last time, and basically we have played in the class coming up with all types of arrays of data that we could have in petroleum engineering or otherwise. This is not just petroleum engineering problem. This is a problem for everybody doing science and engineering. So in general, we organize data in some sort of arrays, and those arrays could have just be a string of data, which is like one dimension, or they can have some spatial dimensions, in which case we start getting multiple dimensions. It could be 2D, 3D. I could also have time, 4D. Beyond that, it's extremely hard to visualize, but definitely exists. Right? Any Excel sheet that you've ever seen is essentially a bunch of data. Often, the ones that we're going to deal with in terms of linear algebra are numerical data sets, right? So they have only numbers. But that said, there could be text involved in the data as well. And often we do actually have to, kind of juggle with both. As an engineer, I love a number because I can compute with number much easier. And linear algebra actually allows me to do so. However, a lot of information is actually descriptive. It could be a name of something, and that could be part of the problem. Or we have to work with geology and subsurface. A lot of that is described. Okay? When we look at the reservoir quality, we look at the amounts of quartz, feldspar, and lithic fragments. Yes, I kind of decide first I have to measure it up, but then after that there's a name describing it, right? And I have to work with that. And that's also like often like I can just like keep talking about something to describe, giving it a number that compares to others in the same group is a difficult thing. Speak about grading, right? I'm trying to put a number on you and your knowledge, right? And that's not always a straightforward thing, and you will argue with me in my judgment and what that number should be. Okay. So we can see that sometimes information comes in different forms. Numerical form is the easiest one to deal with, but it's not the only one. But in linear algebra, we're going to restrict ourselves to numerical data with the understanding that often data actually, these matrices could actually have the data that is not necessarily just in numerical form. All right, so we're going to basically learn linear algebra manipulates with data. So in that sense, the simplest thing that I could have is an array, one-dimensional array of numbers, but I can already kind of think about it as a column of data or row of data. And that's already fast-forward thinking into embedding this into multiple dimensions. Here I could have a row of pixels. I could have a column of pixels in this screen. Right? And obviously orientation matters because if you flip it over, you can't read. Or you have to flip yourself to read. Right? So orientation does matter. So we have to be sensitive to how data is organized. Okay? Now, if I have the same number of elements, I can do operations on it. So we went through this. It's easy basically to go element by element, and we kind of work with standard operations on corresponding elements. So 2 minus 1 will give me 1, okay, in the spot number 1 here. 1 plus 1 will give me 2. 0 plus 5 will give me 5. Okay, so addition and subtraction is easy. Multiplication by a scalar would multiply all in the column or row in this vector. So if I multiply this first vector by 2, I get 2 by 2, 2 times 1, and 2 times 0. So I would get 4, 2, and 0. Okay? That's multiplication with a scalar. That said, scalar and a vector of possible more than one numbers are two different objects. Okay? They have two different dimensions, but we are kind of saying like, well, here's a rule of how you do this. Okay? And then vector transpose will basically convert row to column. Again, that's when dimension matters. Then I will actually flip. I will flip them by transposing. Now, when I generalize both multiplication with scalar and this subtraction or addition, I will get something that we call linear combination. And basically, I have a scalar alpha multiplying first vector plus a scalar beta multiplying second vector. I go element by element, and I multiply all of the first vector with alpha, and multiply all of the second vector with beta, and I add the two, and I get the result. This is kind of like, oh, I defined an operation. It's a straightforward definition. It's kind of easy to learn. But it underlines how we express everything. When I say in spatial dimension that my coordinate, let's say that I'm standing here. In order to know coordinates, what do I need to know? How do I assign coordinates? So I need axes, and I need wherever those axes intersect is my origin. Right? So let's say origin is over there, okay? And I'm standing right here. My z is 0 on the ground. I have agreed that this ground is 0 and not the floor below it. Right? So we have to agree on starting point of the coordinate system, as well as how axes will work. Okay? And once I do that, then a vector that describes my position, okay, is, I need a unit. Let's say the door is a unit. I'm approximately 5 units this way, 1 unit up, say, okay, and 0. So 5, 1, 0 in the coordinates. So I have to define a coordinate system, and where's my starting point? If you give me a different system, the vector describing me will be different. However, if I want to work with anything, if you think about GPS, if you think about your phone knowing where you are, if you think about driving directions from somewhere, we have to have coordinate systems and we have to agree on it. But once you agree on it, my position is a linear combination of unit vectors. It's a 5 times the first unit vector plus 1 times the second unit vector plus 0 times the third. And I only have 3. Okay? So I cannot have, in 3-dimensional space, I only have 3 independent vectors. Every other vector is a linear combination of these 3. That's underlining this. That's a very powerful notion. And that's how we set up how we measure the world. Okay? And how we relate and measure both how the world is, where it is right now, and how it changes. So derivatives are derivatives in the world of the coordinate system that you describe. In petroleum engineering, we don't live necessarily in coordinate axes that are x, y, z, what we call Cartesian coordinate system. Our wellbores are cylindrical, last time I said. So, cylindrical world can have a cylindrical coordinate system that is tied to describing something with the radius distance from the origin. Okay? Then sort of a vector in which you're pointing, as well as the height, z. We are on this earth. If we did space engineering, or something related to Mother Earth, we'd be in a sort of a spherical coordinate system. Not perfect sphere, but nevertheless. So if I'm busy measuring distances of ships going from Houston to somewhere in the world, give me another point, I don't know, south of Africa, Johannesburg, okay? You better measure that distance on a sphere, otherwise you'll be really off, okay? So coordinate systems are important, and actually this is at the foundation of the description of a coordinate system. So once I have a set of independent, typically in 3 dimensions 3, right, spatial dimensions, then that everything else can be described by this linear combination of coordinate vectors, which is a powerful thing. Yeah. All right. So what is, can you take a piece of paper and just do this quickly so that I can test. So A, can you do the operation? And what is the result if you can't? So what is the result of the first one?
-1, 4.
Okay, so that's 2 plus 3 times minus 1 is 2 minus 3, that's -1. And then 1 plus 3 times 1 is 4, right? Okay, what's the next screen? I'm going to interpret this as green, so it's kind of floral. Anyway, so what do I do in the second one? Formally, I can't do that. I have two different objects. I could multiply them based on the definitions I gave. So I gave you certain rules, and based on those rules, the answer is no. There's rules, and then there's implementation of the rules. And we'll see that programming environments, in order to make it easy on us, typically program this addition as possible. And what they often do, but not always, is that you can just add 3 to all of the dimensions. Just to simply as a shortcut, but not a mathematical rule. Okay? So again, there's mathematical rules or theoretical rules, and then how we implement them. In life in general, there's always a difference. Okay? So, what about the third one? Who's another green? Where's my next green? Middle over there?
You can't do it?
You can't do it because they're technically, the way they're written, they're different objects. They have the same number of elements. Okay? And based on implementation, it might be possible. So we are going to work in Python. Python, for instance, says all of these things, unless you strictly define these as matrices and two-dimensional objects, if you're defining them as just an array, it doesn't care whether it's a row or column. It's gonna, as long as it has the same number of elements, it's going to do it. But that's an implementation thing. Okay? This way, strictly speaking, mathematically, no. So if you encounter this in your homework, you can tell me. Math says, or rather telling you, if he's grading, math says we can do this operation, okay, or cannot do this operation. Then we're going to actually, this handwritten homework that is going to be assigned either today or on Monday, to be decided today, depending how far we go. Basically, based on that, you're going to decide whether you're going to see and redo that in Python, and certain operations you'll be able to do, even though math said no. Okay? So there's, again, there's rules and there's implementation. And one has to be sensitive about that in computational environments. They also actively change. So computational environments, they evolve to be easier. Okay? So ability to add 3 to this is just this shortcut to be easier. You could probably encounter a number of shortcuts on your computer. You press something, you have no clue what you've done. Something got executed, right? Because there is a shortcut. So they can be sometimes powerful, sometimes you do them, and you know that you did them. I do that all the time. Then I'm like, what on earth did I do and how do I undo it? Right? But that's a shortcut and that's an implementation that depends from computer to computer. That's not necessarily theoretical. Okay. Alright, so next operation that is useful in a lot of things is so-called vector inner product. And it's going to lead us to how to multiply matrices. Okay. So technically, if I have 2 vectors, I can just focus on this formula. As long as I have arrays of the same number of elements, I can execute this sum. I take first element of the first vector and first one of the second, multiply them, then proceed and add to the multiplication of the second elements, third, and fourth. Excellent. So basically, I can do that. Now, what we also visually do when we embed mentally our vectors into matrices, I can do that if I have a row vector and a column vector. Okay. Then I go x1 times y1 plus x2 times y2 plus x3 plus times y3 plus x4 times y4 is equal to that sum. However, if I flip and have a column vector times a row, my result would be a 4 by 4 matrix in this case. So dimensionality in 2 dimensions matters. If I'm viewing these as one-dimensional objects, it doesn't matter. If I'm viewing that as 2-dimensional objects, so that's a context. Okay? And context matters. And again, on your homework, you can say, in the context of 2-dimensional arrays, this operation can be done and results in a scalar, okay, one number. But we're going to flip this, and in the context of matrices, if I have a column times a row, then it cannot be done as a vector inner product. Okay? So that's when, in the context of dimensions, it matters. That says if I just look at this sum, as long as I have the equal number of elements, I can do it. Okay. All right. Now we actually talk about norms, so we need to measure things. Obviously, I have introduced the importance of having multiple dimensions, and a lot of our data is multidimensional. How do I compare it? Okay. Grades in a class are one dimension, so I can easily compare grades. Or rather, they're A, B, C, D, but they have a numerical value, and I can compare those numerical values. And I know who's greater, who's smaller. What do I do in vector world? How do I compare position standing here and her position in the same coordinate system? And what am I comparing? Okay. So one thing is sort of a length of a vector, okay, its absolute value. Again, we need that origin to know that. Okay. So understanding that the origin is there, I'm certain distance from that point. And she has a different distance to that point, and I can compare those distances. So those are what we refer to as norms. But norms can be different things. And we're actually the ones in charge of the norms and how we compare norms, and what it is that we want to compare. Okay? So sometimes we create what is the norm that I'm comparing different objects by. So I'm going to introduce some general rules that norms have to be obeyed to be mathematical norms. Beyond that, it's really up to you to figure out which norm you want to use, what it is that you want to do with it, and how is it useful to you. You're the engineer. Okay? So, for instance, absolute value is the simple. I will have this measure of a magnitude for vector, and this measure can have different rules. Let me just get to the general rules that they have to obey, and then I'm going to give some examples. I want these measures to be positive. I want only what I agree as a zero vector, that origin, to have a zero value. Everybody else some positive value. If I multiply a vector by a scalar, I'd like the norm of that multiplication to be absolute value of a scalar times norm of that vector. Okay? And then this is so-called triangle inequality. If I add two vectors, the norm of that result should be less than or equal to their individual positions. Those are all of the rules that a norm has to obey. Now let's look at some different norms. Okay. So I already had this example. If I have a clear coordinate system and a point in that system, I draw a vector from the origin to that vector. Vector in itself has both a length and direction. Okay? But I look at what we call Euclidean or geometric length. And in this case, I have 3, 4. So basically, square root of 3 squared plus 4 squared is 5. So that's the norm or norm of my vector. We call this general Euclidean norm. Euclid talked about it first time back in the more generally L2 norm because I'm squaring things. And by the same rule, if I change this square to something else, like 3, and I take third root, okay, of x to the 3, or first absolute value to the 3 plus absolute value to the 3, I'm getting a norm. That norm obeys the rules that I mentioned. Okay? So any number here, I could have L3, L5, L7, and so forth. Mathematically infinite number of combinations. That's fun for mathematicians to play with. But we really need 3 of those because they're useful in practical ways. So Euclidean, I mentioned already. I could also have, and basically technically the way I'm computing it when I have multiple numbers, not just 2 or 3, I square all of the components, sum them up, and take the square root. Okay? So that I can do in 7 dimensions, though only in 2 and 3 I can visualize that distance, right? In 7 dimensions it's getting. But that's how far apart things are in the world ruled by this Euclidean norm. Now back to my example of a ship going from Houston to Johannesburg, or a plane flying. Is that a straight line? Does this Euclidean distance work? No. So I have to come up with a different norm to measure that distance. Otherwise, I'm not going to have enough fuel. That's a very real problem. Okay. Second part is we are in the cities. We are on a grid. Did you fly over here this morning? No? So you were on that grid, however regular. It's not always a regular grid. In Manhattan, maybe it is, but here, sometimes it is, sometimes it's not. And whoever came up with a 38 and a half, it's amazing. So anyway, so it's not a regular grid and doesn't always make sense. 38 and a half, that starts as a 38 and a half in East Austin, then it changes to 38, and then to 35th somehow once you cross Lamar. Have you noticed that ever? And meanwhile, you're on the sort of the same street going through. So back to the regular grid. So assume you're a regular grid, you've got to measure distance. If your Google Maps or whatever maps you're using, they have to constrain themselves on those streets and measure real distances. So the regular Euclidean distance as a norm of a distance, it doesn't work unless you're really directly flying. So we have to come up with some others. So more general way is to replace 2 with any number p, and we call those p norms. In so-called, if p is 1, I have just sum up the absolute values. And that's actually what works on the regular Manhattan grid. So let me actually show you that example here. So let's say that I am on a true regular grid. Okay. Distance from this point to over there is basically however I take this in this well-connected street, on these well-connected streets, I can take this distance plus this, which is essentially absolute value of my first coordinate plus absolute value of my second coordinate, right? So if this was 1, 2, 3, 4, 5, 6, so this is 6 plus 6, it's altogether 12 blocks, or 12, and that's my distance. That is actually what we call one norm, just absolute value of all of the coordinates summed up together. And it's also one of these P norms. Now, I could also have so-called a max norm, which is really, you get this mathematically, when you take P goes to infinity, okay? So it's a very large number. Let's say that it's 1,000. 1 to 1,000 and 1,000 to 1,000. How those two numbers compare? Very much. 1,000 takes the, right? So very large numbers, when P is very large, take the cake. Okay? And the rest of the small stuff doesn't matter. So technically, if you take kind of like mentally, you take a limit of that, what you will get here is a 1,000th root of a something to 1,000, something large to 1,000, which is that number absolute value. So basically, what we call an infinity norm is just the maximum of all of the elements that you have in the array. That said, there's a lot of practical, that's mathematical definitions. In a lot of practical situations, it's a good thing. Like I'm looking at the worst case scenario. So my worst case scenario is 1,000. Okay? And when I'm looking for it, I'm actually looking at L infinity norm or max norm of things. I measure things by the worst case. So it depends on me what it is that I want to measure. Here's another example that is basically environmental engineering example. You know how water restrictions work in Central Texas, Austin in particular. So we are measuring availability of water in Austin by the availability of water in the water reservoirs, which is basically dams on Colorado River, okay, upstream. So those, when it hasn't rained for a while, the recharge of those reservoirs hasn't happened because there's not enough water. And that we measure the level and the amount of water in the reservoir. So basically the total availability of water is basically when you sum up all of those reservoirs, yes? So if I have 3 lakes or 2 lakes, let's do 2 lakes, Lake Travis and Lake Buchanan. Okay. If I sum up their volumes, what norm am I using? I just sum up the absolute values of one norm, right? And my vector is just basically a vector of each corresponding line is corresponding to a lake, in this case 2 lakes. Yes? So you come up with vectors and you come up with measures of those vectors. So I have come up with my 2-dimensional vector world. One is the volume of lake, the first element is volume of Lake Travis, and the other one is Lake Buchanan, and I sum up it. And when that value, that sum, which is norm of that vector, drops below a threshold, then I have alert. Alert email goes to appropriate people in Austin. Okay? And then radio advertises, do not water your lawns, or just water them based on the restrictions appropriate for the level of the use. So decision making in engineering, what I'm pointing out is decision making in engineering depends on how you set up your vectors and norms, and who is in charge of setting those up. So it goes also through approval process. So engineers come together, discuss, and then approve, right? And sometimes put to a citywide vote. Okay? But it's engineers that come up with the first design. So it might be your job to come up with thresholds for whatever operation that you're going to work on, maybe not in this, but something similar. Okay? How do we set up the rules? How do we automate something? We need thresholds. And how do we act on certain threshold being this or that? Okay? So you define how to measure things and how to work. So this is just a little bit of too much text, but this is also working as your notes. So just as a note, if you're the one deciding how to measure things, okay, then often this max norm is taking the largest number, so sort of the largest number overtakes. Depending on the data, if you don't trust the measurement, or trust all of the measurements, and there's a lot of uncertainty, you don't want the largest value to take the cake, because it might be error. Sometimes you don't like outliers. We call those outliers, either too small or too big. So to guard yourself against that, if you need to guard yourself, you're going to not use L1 norm. You're going to decide to use it, or L infinity norm. You're going to use the different one. So that's something that you need to think about, because you have a choice of norms. How do you design is depending on what do you want to pay attention to, what is important, and how is your data looking like. So that's something to think about. Okay. Now this is just the fun. Geometrically, this is a circle, eh? Is this a circle? Sure. And now one norm. Is this a circle? definition of a circle is that my distance or a norm from an origin is 1. Yes? A circle of radius 1. Yes? Well, let's do L1 norm for this. This point right here, let me actually show it on a video. This point right here, its norm is, let's say that's 1/2 minus 1/2, yes? What is L1 norm of point 1/2 minus 1/2? So this point right here, it's on a circle of radius 1 in L1 norm. If I'm measuring distances using L1 norm. Same for this point and any point on this line, because this line, by the way, is line of 1 minus x1, the coordinate 1, right? Same thing here, same thing here, same thing here. This is a circle in L1 norm. So norms define how we measure things, but also how we kind of optically see things. Okay? Have that in mind. It's a fun thing to see geometrically the difference between the norms. Roll that back? Okay. Let's say that I'm measuring distances in L1 norm. That's what maps do. If you're on a, what we call Manhattan grid. Let's say that our city is laid out on a regular grid. Okay. So technically, okay, in this world, to get to this point on sort of a more regular grid, you gotta do this plus this. So your distance is 1. The distance that you actually have to drive. Even though aerial distance is not 1.
I think your mouse is like offset wrong. Yeah.
Let's see.
Yeah, look at the screen while you're doing that.
Oh, hi. Wow. It's mirroring or something. Okay, forget the mouse. This point right, I'm tall, I'm not that tall. Okay, this point right here, its coordinate is 1/2 minus 1/2. To get to it on Manhattan grid, I need to go 1/2 this way, 1/2 down. That's 1/2 plus 1/2 distance. Okay? I can't get over there, I gotta go this way. Well, I'm using energy to go this way, or fuel if I'm driving, right? So my distance is actually 1, not this aerial distance. I don't fly yet.
So when you do L1 norm, you do an absolute value of the coordinate and then add them?
Yes. Then this is how circle looks like in that norm. I mean, just the visual representation. Because circle is a geometrical set of points that are distance 1 from the origin in this case, right? Or some distance. But it's cool to look at this thing. In infinity norm, okay, all of the points in this line, all of them have infinity norm 1, because the maximum coordinate is 1. The other coordinates is between -1 and 1. So it's kind of cool. It's just a geometrical representation of what I was saying. We measure things differently, right? Depending on how your glasses are working, right? Anyway, this is just a fun point. But I actually had an aid here. So again, on this is the same. My mouse is mirroring. So basically this point, and then it's also not moving. Anyway, I'm gonna forget the mouse today. I don't know what's going on. Anyway, so I could have different norms. Yes.
What exactly is L infinity?
It's just a name for a maximum norm, and that's the norm in which case I look at the vector. I take the value of a component in an absolute terms that is the largest. Just maximum value out of the absolute values of all components.
So that square is 1 all the
Yeah.
way.
Yeah. Because the rest of the other coordinate is between -1 and 1, right? So the one that is 1 is the largest one. Yeah? All right, excellent. Another thing that we need to measure spatially is orthogonality. Okay? And if I ask you, just like on this screen, I'm going to borrow it for a moment. Great, this line is orthogonal to this one, that's 90 degrees. The question is, can we generalize that, and how we do that for vectors that are not in our 2 or 3D? So what we do is we take what is a scalar product or inner product of two vectors, okay, and just divide by their norms. In this case, I am using Euclidean norm by convention, this regular norm. I know I've bent your view on norms. Now I'm bringing it back to the regular one. And that's again just a convention, though you could technically define it differently. And the cosine of the angle between those two turns out to be given this. And if I'm in 2 or 3 dimensions, this actually works as we would expect it to. If something is at 90 degrees, it is at 90 degrees. Okay? In 4 dimensions or 5 dimensions, I don't know how to visualize two things being at 90 degrees from each other, but I do have a mathematical expression for it. Okay? All right. Now I can also normalize. So often when I'm asking about direction, I don't care about the value that the vector has in any norm. So I can normalize by it. Okay? And those, when vectors are both orthogonal and their norm is 1, I call them orthonormal. And that's our coordinate vectors, is an orthonormal set of vectors. Okay? So in Cartesian coordinate system, my 3 coordinate vectors, they're all mutually orthogonal to each other, and their absolute values or their norm is 1. All right. So, question for you is, if I have a vector 1, minus 1 and a vector 1, 1, are they orthogonal? So what is the scalar product of them? It's 1 times 1 plus minus 1 times 1. So it's 1 minus 1. Scalar product is 0. What is the cosine theta, therefore, has to be 0. What is theta if cosine theta is 0? So basically, the vectors that are orthogonal to each other, their inner product or scalar product is 0. And that's useful in 2D and 3D when that's actual orthogonality, but it can be also useful in generalized data processing when I have very large vectors. And if I wanted to convert this vector to a unit vector, a vector of length or absolute value 1, what would I do? So what is its norm in 2 norm? It's square root of 2. So basically a unit vector will be 1 over square root of 2 and minus 1 of square root of 2. They're so-called collinear. They're pointing in the same direction. And they're parallel. They're on top of each other. Just one has unit 1 and the other one has whatever length it has. All right. Yeah. Now we move to matrices, and now we have to define matrices. Okay. We're typically going to use uppercase Roman letters for them. And the difference is that I have now multiple rows and columns, and I have to kind of be aware who is in the row, who is in the column. Sometimes it matters, sometimes it doesn't. But again, in this screen has an orientation. And if I flip rows and columns, you are not going to be able to read unless you flip yourselves too. So it's kind of important and kind of not important depending on application. Sometimes things are symmetric and it doesn't matter, but in this case, it does matter. If the screen was empty, you can flip it. You couldn't care less. But if it has certain structured data within, then it does matter. Okay? So matrix is either, and you can look at it either as a collection of rows or collection of columns. Depends how you read. Okay? Often depends how you read. In the alphabet that we're using, we are reading from left to right. And we read first row, then second row, third row, so forth, by convention. Is that how the entire world reads? Can somebody think about a different way to read? From right to left? Anyone? Column-wise? Japanese. It's a matter of agreement. Which one's right? We just have to know what the agreement is so we can actually read, right? So there's no right or wrong, okay? It's a matter of convention, and that everybody who is in the same room trying to communicate that they agree to the convention, okay, and know what to do or how to translate if translation is needed. So again, I can view matrices of numbers either as collection of rows and columns, okay, as long as I know what I'm trying to do and how did somebody write it so I can read it the same way, you're good. Okay. When you write it one way, read it the other, what you get is a scramble that means nothing. And computers often do that. Okay. So if I have written all of my data about a reservoir, row by row, and you come in and read it column by column, good luck. You're not going to drill to the target. Okay? So we need to know how did we agree to store the information. Okay. Now I want to do with matrices just like I want to do with vectors. I want to add them. I want to multiply. I might want to multiply different objects. And now, because of the dimensionality, it becomes a little more involved. With scalar, easy. I can multiply everybody in the matrix with the same scalar. Fine. We can do that the same way we did with vectors. But how do I multiply a matrix and another matrix? So I have to implement some rules, and their dimensions have to match, and that's what we're going to do on Monday. And also, I need to know whether I can multiply a matrix and a vector. Again, there has to be certain matching of dimensions, otherwise good luck, and I need to know a rule how to do that. Okay. So that's what we're going to do. And then we'll always be able to transpose the matrix just by flipping it, which obviously is sometimes important. Okay. So we're going to do some examples next time and look for the homework assignment.